Alrighty, in this video we are going to talk about parametric equations. Now remember back in AB whenever we did PVA, our particle was either moving up or moving down or moving left or moving right, and there wasn't really a curve where we were both moving in both x and y direction. So what we're going to have here is a third variable, t, where she's going to be controlling x and y. So she is a controller. As t varies, x and y will also vary and trace out some curve c, which is going to be called the parametric curve. To write a parametric equation in rectangular form, we have a process called eliminating the parameter, which hopefully you guys did back in pre-calc. So today's lesson here is essentially a little bit of pre-calc review that won't be tested on the AP exam, but we'll kind of need that in preparation for what we'll be doing in the second lesson and the third lesson and whatnot. So for number one, we are going to go ahead and sketch this lovely parametric equation where here we have x is equal to t squared minus 2t, y is equal to t plus 1, t is being controlled being a -2, -1, 0, 1, 2, 3, 4, and calling it a day. So here we are going to get, if I were to actually evaluate this, I'm going to get 3, 8, 3, 0, -1, 0, 3, 8. Make sure that you actually verify that actually works. Same thing here. I'm going to get -1, 0, 1, 2, 3, 4, 5. And then if I were to graph this on my lovely xy coordinate, I'm going to get, let's see, 1, 2, 3, 4, 5, 6, 7, 8. -1, 3, 0, 0, 1, -1, 2, 0, 3, 3, 4, and then 8, 5. One important note about this is that whenever we are sketching this, make sure that you have arrows pointing in the direction that we are going. Notice how here, whenever we had a t, at -2, we started at 8, -1, and then we kind of went left. So make sure that my arrows are going like this until we hit our vertex of -1, 2. So right here, this right here is our sideways parabola. And to write this in rectangular form, we are going to eliminate one of the parameters. To eliminate one of the parameters, it's going to be easiest to solve for t. So looking at this one, I'm going to solve for t here for the y is equal to t plus 1 and just solve for t. If I solve for t, I'm going to get y minus 1, which means that whenever I substitute in t back into my equation here, I'm going to have x is equal to y minus 1 squared minus 2 y minus 1. Now, theoretically, you could just keep it like that. However, I do want to show you guys how we are getting two y-intercepts of 1 and 3. Notice how here that whenever I do this, I can factor out a y minus 1, which means I'm left with a y minus 1 minus 2, which means that I'm left with a y minus 1 and then a y minus 3. And that right there is basically your factored form of me getting a y-intercept of 1 and a y-intercept of 3 for my little parabola right here. All right, for number 2, we want to eliminate the parameter. So what I'm going to do here, once again, I'll probably solve for t here. That's going to be the easiest for us. Y minus 3 over 2 is equal to t. Once you do that, just substitute it back in. So x is equal to y minus 3 over 2 squared plus 1. And just call it a day. All right, we are going to eliminate the parameter here. Just think about which one's easiest for us in terms of solving for t. Personally, just because this is x is equal to ln of t, I could just e both sides. So then t is equal to e to the x. and then y is going to be equal to 2 e to the x square, which is the same thing as saying 2e to the 2x. Now, hypothetically, theoretically, if you wanted to solve for t here for this right here, you could also do that. That's fine. All right, so that was just a little review of eliminating the parameter. What we're going to do now is basically use the chain rule for parametric equations to get this lovely derivative right here. Now notice how here that whenever we are taking the derivative, we are taking the derivative with respect to t. Now because we have the derivative with respect to t, I gotta use chain. So I'm gonna have dy dt is gonna be equal to dy dx times dx dt. And then if I'm solving for dy dx, my derivative, that just gives me this thing right here. So me dividing dx dt, dividing dx dt gives me dy dt over dx dt. All right, just like basic analyzing that we did back in Unit 2, we could also do some basic analyzing here for local minimums and local maximums. So for 4, we have a particle such that x is equal to t plus 1 and y is equal to 1 minus t, 2t squared for 0 to 4. What point corresponds to a local maximum? Use the method of finding the derivative in terms of t to solve this problem. So what I want to do here is find out what the derivative is in terms of t. So I got to use dy dx is equal to dy dt all over dx dt. Well, we know that dy dt is going to be negative 4t. And we know that dx dt is just going to be 1. Which means that dy dx, my derivative here, is going to be negative 4t. Now, if dy dx is equal to negative 4t, I'm going to set that equal to 0 because I need to find a critical point. And if I have a critical point here, that is going to be, guess what? T is equal to 0. Now, if t is equal to 0 here, and we have negative 4t, I know going to the left is going to be positive, and going to the right will be negative, which means that we will have a relative maximum at time t is equal to 0. Well, not time, because we don't know if it's actually time or not, but it's going to be t is equal to 0. Now, notice how here, I'm asking you guys for a point, so whenever we are looking at this, we want to make sure that we plug in 0 back into my rectangular equation of x is equal to t plus 1 and y is equal to 1 minus 2t squared. So if I plug in 0, I'm going to get 1, and then if I plug in 0 again, I'm going to get 1. So this tells me that I have a relative maximum at 1, 1. If I were to use finding the derivative in terms of t. Number 4 is going to be the most preferred method that you guys use because sometimes you might not be able to eliminate the parameter, unfortunately. But for this one, we are able to eliminate the parameter, so that's why we're doing number 5 here, where it says find the derivative in terms of x by eliminating the parameter. So here, we know that if I have x is equal to t plus 1, I'm probably going to have t is equal to x minus 1, and then using substitution, I get y is equal to 1 minus 2, x minus 1 squared, which is my rectangular equation. Using basic derivatives now, dy dx is going to be equal to negative 4 x minus 1, which means that if I were to set this equal to 0, x is equal to 1. Now, based off of this information right here, if x is equal to 1, and using my derivative, this left side is going to be positive. This left side is going to be negative. We have a relative maximum again. And because I already know that x is equal to 1, I could just figure out what y is by substituting it in. So if x is 1, substituting it into y, that's just going to cancel out, and I'm just left with 1. So this numbers 4 and 5 was just a good introduction on how we could use what we did back in earlier units in AB with parametric equations. Obviously, you're not going to see something like number 5 whenever we have parametric equations. You'll probably have to do something like number 4 where we have dy dt and then dx dt. All right. Number 6 is going to be our last problem, and this is going to be a good introduction to what we'll be doing in class in terms of finding the arc length. But here, we want to sketch and identify the curve defined by the parametric equations x is equal to cosine of t and y is equal to sine of t from 0 to 2 pi by filling out the table. Well, if cosine is 0 and sine is 0, then that's going to be 1, 0, which is right here. If t is pi over 2, then x is 0, and then y, sine of pi over 2 is 1. So now I'm up here. If t is pi, I'm going to have negative 1 and 0, which means I'm right here. And then if t was 3 pi over 2, I have 0 and negative 1, which brings me down right here. So you'll realize that whenever I trace out this curve, this should be familiar, aka the unit circle. And then it's asking you what's the distance traveled by a particle from 0 to 2 pi. Well, the distance here is just going to be my circumference. And in this case, if I have a unit of 1 here, then my distance is just going to be 2 pi. Now, what we're going to be doing next in class is figuring out what the arc length formula is, and then using that formula to help us with number 7 and number 8. And then we'll move on to the parametric equations of calculus.